It is time for Chapter 3, Section 6, and that is polynomial and rational inequalities. Instead of equalities, now we'll have the good old greater than and less than signs in there. Not many objectives, and we'll wrap this section up in 2 days in class. Solve polynomial inequalities, we'll solve rational inequalities, and solve problems modeled by polynomial or rational inequalities. So first we need our definition of a polynomial inequality. And a polynomial inequality is any inequality that can put into one of these forms. Some function f of x is less than 0, or the function is greater than 0, or maybe less than or equal to, or greater than or equal to. In this section, we establish the basic techniques to solve polynomial inequalities. We'll also use these techniques to solve inequalities involving rational functions. So graphs can help us visualize the solutions of polynomial inequalities. For example, the graph of this inequality, or this parabola, x squared minus 7x plus 10, is shown here in the figure. The x-intercepts 2 and 5 are boundary points between where the graph lies above the x-axis, shown in blue, and where the graph lies below the x-axis, shown in red. So remember, the y-axis is the value of our function. If we are negative valued, we're down here underneath the x-axis. And if we're up here in positive y-value territory, we are above the x-axis. Locating the x-intercept of a polynomial function f is an important step in finding the solution for polynomial inequalities in the form of less than 0 or greater than 0. We use the x-intercepts of the function as boundary points that divide the real number line into intervals. And the real number line is nothing more than the x-axis. So we're going to chop our x-axis up into intervals. On each interval, the graph of the function is either above the x-axis, greater than 0, or it is below the x-axis, f of x is less than 0. For this reason, x-intercepts play a fundamental role in solving polynomial inequalities. The x-intercepts are found by solving the inequality, or the equation, f of x equals 0. And we've been doing that for a better part of the school year. So we have a procedure to solve these polynomial inequalities. Step 1, express your inequality in this form, either less than 0 or greater than 0, or you could have the or equal to under there. You just want a 0 on one side, everything else on the other. Step 2, solve the equation by setting it equal to 0. Most of the time we're going to have to factor and set each factor to 0. When we do this, we find the solutions that we are going to call the boundary points. Step 3, locate the boundary points on the number line, thereby dividing the number line into several intervals. In each interval, we are going to choose one representative number. That'll be our test value in that interval. And we are going to evaluate the function at that number. If the value of f is positive, then f of x is greater than 0 for all numbers in that interval. If the value of our test number is negative, then f of x is less than 0 for all other x values that are also in the same interval. Step 5, write the solution set, selecting the interval or intervals that satisfy the given inequality. This procedure is valid if less than is replaced in less than or equal to, or if the greater than is replaced with greater than or equal to. However, if the inequality involves less than or equal or greater than or equal, include the boundary points in the solution set. So if we're writing it with interval notation, if we have less than or equal to, we'll use brackets. If it's strictly less than, we would use parentheses. Again, the or equal to, we use the brackets to show that those points are also a part of the solution set. All right, example 1. Solve and graph on the solution set on the real number line of 2x squared plus x is greater than 15. Okay, I'm going to move my number line up here a little bit, move this up. We really only need to see the inequality now, and I'll put my number line up here. Step 1 was we wanted to get 0 on one side, everything else on the other. My 2x squared is positive here on the left, so I'm going to keep everything here on the left. And I'm going to subtract 15 from both sides. So now it's minus 15 is greater than 0. Okay, step 2, we want to set it equal to 0 and factor it and solve it. So for step 2, I'm going to write it as an equality now. 2x squared plus x minus 15 equals 0, because we want to factor it and find our boundary points. Okay, 2 is prime. The only way that'll work is 2x and x. I need the factors of 15. The most common used there are 3 and 5. And whatever I put over here gets multiplied by the 2. I want a 1 in the middle, so this is probably going to be a 3, because that'll be a 6. And then I'll have my 5 over here. So let's see, my outers multiply to 6x. My inners multiply to 5x, and the difference between 5 and 6 is 1, and I want it to be a positive 1, so I want a positive 6, which means this here will be an x plus 3. The other one will be a minus. Oops. Plus 3 minus 5. Let's double check. That's positive 6x minus 5x is positive 1x. And then negative 3 and positive, or negative 5 and positive 3 multiplied to the negative 15. All right, we set each of those separately equal to 0. 2x minus 5 equals 0. We'll add 5 and divide by 2. X is 5 halves. The other one is much easier. Just set it equal to 0, subtract 3 from each side. X is negative 3. So our boundary points, I will abbreviate BP. Boundary points are negative 3 and positive 5 halves, or 2.5. Guess we'll get rid of that. So we found our boundary points, and I guess we can mark those on the graph. Negative 3 and 5 halves is 2.5, so right in between 2 and 3. So now we have these intervals. Here's an interval from negative infinity to negative 3. We have another interval from negative 3 to 2.5, and then from 2.5 off to infinity. So we're going to pick a test value within each of those intervals and test it back in the original inequality. So let's see here. I guess that was our step 3. Our boundary points chopped up intervals. So I'm going to do it like this. Here we have our interval. That's a very terrible R. And we had our first interval goes all the way from negative infinity to negative 3. And then our next one went from negative 3 to 5 halves, or 2.5. And then we went from the 5 halves off to positive infinity. In each interval, we're going to pick a test value. We're just going to pick one number that lives on that interval, and we're going to test it. So from negative 3 to negative infinity, I like to work with nice numbers, and for me 10 is easy to work with. I can square it and multiply it by other numbers very easily in my head. Between negative and positive, there always exists the number 0. That is a great test value if it is on your interval. And then from 5 halves to infinity, again, I like to work with nice numbers like 10. So we want to evaluate the function at those test points. And when I say evaluate, I'm looking right here, underlined in blue. We want to see if we plug in the test value, is this inequality true or false? That will be our conclusion. So let's see, if I plug a negative 10 in here, I'm going to square the negative 10 and get 100 times 2 is 200. 200 plus a negative 10 will be 190. 190 minus 85 is a positive number. So we come up with a positive number. Is that positive number greater than 0? Yes, it is. It's true. So that will be part of our solution set. We can go to the number line now from negative 3 to infinity as part of our solution. So we'll put a parenthesis here at negative 3, and we know we're headed off toward negative infinity. All right, let's try the next interval. This is a nice easy one. 0 was our test value. So 2 times 0 squared plus 0 is 0. Minus 15 is a negative 15. Is a negative number greater than 0? Well, that's false. So we are not going to color in that interval on our number line. Last interval, 5 halves to infinity. Again, I like positive 10. So that'll be 10 squared is 100 times 2 is 200. Plus 10 more is 210. Minus 15 is positive 195. A positive number is greater than 0. That's true. So that will also be part of our solution set. So from 3 to infinity, I will also color in that part of the number line. And now I just thought ahead. I looked in my notes, and I did see this on the next slide. Of course, you saw this in your notes. You know, here's where you'd write in the interval, pick your test value, plug it into the inequality, and see if it is true or false. So again, that's what we did here, and our number line is filled in. Now you can always check this too, or a little intuition. We can check our work or make our lives easier. If I look back to this part, 2x squared plus x minus 15, that is a parabola because it's x squared, and it opens up because it's positive. So we do have a parabola opening up. Remember, the number line is just our x-axis. So we do have a parabola opening up. And remember here our inequality was greater than 0. So where does our parabola rise above the x-axis? Well, we can see right here we transition from below the x-axis. Let me back this up. I scribbled that in too much. And let me do this. Move that down a little bit. There we go. Remember, the number line is just the x-axis. We do have the y-axis here, and it's a positive 2x squared, so it's a parabola opening up. And our inequality was greater than. Where are we greater than 0? Well, that's where we cross above the x-axis. So here we are above the x-axis. That's why we colored in from -3 to -infinity. And we are under the x-axis from -3 to 5/2. And then again, we transition. Now we're back up above the x-axis into positive y territory. So that's why we colored in 3 to infinity. If we were to redo this problem, but with a less than sign instead, we would just reverse everything. You know, on the number line, we would only color in between -3 and positive 5/2, and we would not color in from -3 to -infinity, and from 2.5 to infinity. So again, remember, this is a two-dimensional thing we're trying to represent in one-dimensional space. So always think about there's a parabola in there, and that number line is just our x-axis. All right, I guess we can skip this slide because we should have been filling that in, I guess, as we went through on the last one. Example 2, solve and graph the solution set on the number line. 4x squared is less than or equal to 1 minus 2x. Okay, and we got the same thing here. Alrighty, so on this one, step 1, get everything on one side. I usually get it on the left or wherever my x squared term will be positive. My x squared term is positive on the left, so I'm going to move everything else to the left. I'm going to add the minus 2x, so now over here it's a plus 2x. On the right I had a plus 1, so I'm going to subtract it out of there, and that is less than or equal to 0. Step 2, set it equal to 0 and try to factor it. All right, if I work on this one, I'm going to have a 4 and a 1. 1 is prime. I could break the 4 up into 2's and 2's or 4's and 1's, but the middle term plus 2x is not going to ever work. So we cannot factor it that way. Completing the square would be a lot of work because we got to divide everything by 4 first and then chop that in half. So this might be a prime candidate for the quadratic formula. A is 4, B is 2, C is -1. X equals -b plus and minus the square root of b squared minus 4 times a times c. A times c is -4. All divided by 2 times a, which is 2 times 4. So let's see, what do we have under the radical? -4 times -4 is positive 16, so that'll be 4 times 16, which is 20. And the square root of 20 is reducible down to the square root of 4, which is 2, times the square root of 5. And that's all divided by 2 times 4 is 8. We can reduce, I guess, but when we're dealing with the number line, we do want to plot a point on the number line. You know, the pluses and the minuses and the radicals can kind of throw us off. So you bust out the handy old calculator, and we will get decimals. If we do the positive, -2 plus the 2 roots of 5 all divided by 8, that boundary point becomes 0.3. If we do, and that is when we did the plus in the plus minus, if we do the minus, -2 minus 2 roots of 5, and then divide that answer by 8, we get a -0.8. So those are our boundary points. Boundary points. So actually, because those are such small decimals, I'm going to take this number line and I'm going to chuck it in the garbage. And what I'm going to do is we can scratch our own number line in there we can make much more customizable. Ooh, I don't want a red number line. I want black. Make it a little thinner there. Oh, geez. Back. Black. So here, if you're drawing your own number line, the boundary points are the key, and we want to go a little bit beyond those, so you don't have to go too crazy. If I was making this by myself, I got a negative 0.8 and a positive 3. Of course, I want to put my 0 on there somewhere. I'm going to put 0.3 kind of close to 0. Oop, get over there. And negative 0.8, I'm going to put a little farther over here, negative 0.8. So there's our number line, and I guess what I can do, I'm going to copy that. Copy, hop over here, and paste it, because we're going to need this, I guess, more on this slide. And, ooh, I can do this. Make it a little longer, what the heck. So we have our boundary points. We have chopped up our x-axis, and we're going to plug our test values back into our equation, our polynomial there from step 1. And we have it right here, except they forgot the inequality. That is less than or equal to 0. Less than 0. So our first interval will go from the far left, negative infinity, and it'll go to negative 0.8. And then we'll have another interval go from negative 0.8 to positive 0.3. And then we will go from positive 0.3 to infinity and beyond, just like Buzz Lightyear. All right, test value, good number between negative 0.8 and negative infinity. You could, torture yourself and do negative 0.99, something like that. And what the heck, negative 10, nice number to work with. Again, I can work with it pretty well in my head. I plug a negative 10 in for this x, I square it and get 100 times 4 is 400. Plus a negative 20 and minus 1. That is definitely going to be positive. Our answer is a positive. Are positive numbers less than 0? Well, no, that's false. So we're not going to color in that part of the number line. Between negative 0.8 and positive 0.3, from negative to positive, we always have 0. 0 is a great number. And then we'll have 4 times 0 squared plus 2 times 0. So that'll turn into a minus 1. Is minus 1 less than 0? Yes, that is true. So we will color in that interval. From 0.3 to infinity, I'd use positive 10. 10 squared is 100 times 4 is 400 plus 2 times 10 is 20, 420. 420 minus 1 is 419. Definitely positive. Are positive numbers less than 0? No, that's false. So the only interval we're going to color in is going to be between the boundary points. And, ooh, we did have, I almost forgot, that is less than or equal to. Less than or equal to. So we're not going to use parentheses, we're going to use brackets. And again, we're only coloring in the numbers between the boundary points. So again, let's take this from the one-dimensional x-axis number line to the two-dimensional Cartesian plane. Here's our 0.3 boundary point. And negative 0.8 would be here. And our function was 4x squared. It's a positive 4x squared. So that is a parabola opening up. And our inequality was less than or equal to 0. So we were only interested in where the parabola was under the x-axis. And that's what we colored in here between the boundary points. After we hit the boundary points, we're up above in positive y value territory. And positive y values are not less than 0. So that's why we did not color in those intervals on the number line. And if we were to redo this problem, and the only thing that would change would be the inequality, if instead of being less than or equal to 0, this was done with greater than or equal to 0, we would only be interested in where the parabola was above the x-axis, so that would be from 0.3 off to infinity, and from negative 0.8 off to infinity. And then we would not color in the part of the number line in between the boundary points. So it's all about the inequality, what part of that number line you will be coloring in. Ooh, okay, that's enough for me. Pause the video, try the practice problems, fire it back up, and see if you got them right. Okay. First one, solve and graph. Step 1. Get everything on one side and have a 0 on the other. So now it'll be minus 20 is greater than 0. And then for step 2, we want to find our boundary points by making it equal to 0 and factoring. And the factors of negative 20 that add up to negative 1 are x minus 5 and x plus 4. So we find our boundary points by setting each factor equal to 0. and we'll get positive 5 and negative 4. So we can start working on the graph. Positive 5, negative 4. Okay, let me get rid of, I guess we can get rid of this now. And now we want to test our intervals. So let's see, our first interval will go from negative infinity to negative 4. And then we'll go from negative 4 to positive 5. And then from 5 off to infinity. Values. Our test value from negative 4 to negative infinity, I like negative 10. Between negatives and positive lives 0. And from 5 to infinity, I like 10. So we are next going to evaluate that and then come up with our conclusion. So plug in the negative 10. Negative 10 squared is 100, minus a negative 10 takes us to 110, minus 20 is positive 90, so we have a positive answer. Is that greater than 0? Of course, true. So we will color in that part of the graph. Plug in 0. 0 squared minus 0 is 0, minus 20 is negative 20. Is a negative 20 greater than 0? No, false. So we will not color in that part of the graph. Positive 10, 10 squared is 100, minus 10 is 90, minus 20 is 70, but 70 is still a positive number, which is greater than 0. So there we have again true. So we're not going to color in between the boundary points. We're going to head off to positive and negative infinity. We are strictly greater than, so there will be parentheses. Parenthesis off to the right, parenthesis off to the left. And let's do a quick check conceptually. This again is a positive x squared. Positive x squared is a parabola opening up, so it would look something like this. And our inequality was greater than, so we want, where is the parabola above the x-axis? Yes, we're above the x-axis here. That corresponds to 5 to infinity. We are above the x-axis here. That corresponds to the negative 4 off to negative infinity. All right, good times with graphs. Let's see what's going on here with this one. Right, solve and graph on the number line. And this one, I'm going to throw this graph into garbage because we're going to make our own. We have our 2x squared. It's positive on the left, so I'm going to leave it there. Add 6x to both sides, and I'm going to add 1 to both sides. Now it is less than or equal to 0. And we want to think about setting this equal to 0 and factoring. And before I go down that road, it's going to be impossible. Let's see. I guess I did the last one by quadratic. This one, it's okay with complete the square. I'm going to divide everything by 2. So this becomes a 3x now. And I'm going to divide this by 2, and it's going to be a 1/2. And then I'm going to subtract it from both sides. So now over here, it's a negative 1/2. And I want to set up my perfect squared binomial. Bring down the x, bring down the plus, chop 3 in half by dividing by 2. But then when I square it, I'm going to add it to both sides. So now it's going to be a 9/4. And over here, a plus 9/4. So let's make this into a fourth. 1/2 is 2/4. And that's negative. 9/4 minus 2/4 is 7/4. At this point, we radical both sides. So now we have x plus 3/2 equals plus or minus. Square root of the numerator is radical 7. Square root of the denominator is 2. And then we are going to subtract 3/2 from both sides. So now it will be negative 3 plus or minus root 7 all over 2. Again, just like in the example, that doesn't do us too much good. For our boundary points, if I evaluate this on the calculator, negative 3 plus root 7, get that answer and then divide by 2, you're going to get a negative 0.1. And then if we do the plus version, negative 3 plus the root of 7, all divided by 2. I got that backwards. If we put the plus in there, that is the 0.1. If we plug in the positive, this is getting me even confused a little bit here. If we plug in the boundary point of the positive option, we get a negative 0.1. And if we plug in the negative, negative 3 minus the root of 7 all over 2, we get a negative 2.8. So there are our boundary points. Number line. Again, on mine, I like to at least show 0. And then we got a negative 0.1 and a negative 2.8. Number line is not to scale. So let's see. Oop, I didn't want to erase all of that. There we go. So what are our intervals? Negative infinity to negative 2.8. Negative 2.8 to negative 0.1. And then negative 0.1 to infinity. So, of course, next option is our test value. Here, I like negative 10. Between negative 0.1 and negative 2.8, we could do negative 2 or negative 1. I guess negative 1 will work. Negative 0.1 to infinity, there's where we can squeeze in 0 as our test value. So we're plugging the test values in here. Negative 10 squared is 100, times 2 is 200, minus 60 plus 1 is definitely positive. Is positive less than or equal to 0? No, that's false. So we're not going to color in that interval. Plug in a negative 1. Let's see, negative 1 squared is 1, times 2 is 2. And then we're going to have plus 6 times negative 1 is a minus 6, and then plus 1. 2 minus 6 is a negative 4, plus 1 is negative. Is a negative number less than or equal to 0? Yes, that is true. Now the easy one, plug in 0. The x terms are wiped out by the 0, so we have 1. Is 1 less than or equal to 0? That's false. So we will also not color in that interval. The only interval we color in is between the boundary points, and it is less than or equal to, so we will use brackets. And there, oops, what did I just do? I messed something up. Let me try this. There, it's back. Okay. Get rid of this. Let's do a little quick conceptual check of our work. It is a positive 2x squared, so it is a parabola opening up. So imagine our second dimension with a parabola opening up, and we wanted less than or equal to 0. Where is the parabola under the x-axis? And that's right where we colored in between the boundary points. There we go. Homework, page 420, 5, 6, 7, 11, and 12. Enjoy.